Hello, everyone. 1 second. Hopefully, I have now shared the correct screen for everyone. Fantastic. All right. I have a lot of content to get through, so I'm going to start fairly soon on. I don't know what the general delay has been, but we're gonna crack on. So, if you're interested in learning what's new in Compiler Explorer, you're in the right place. And if not, there is another talk going on in another track, and I'm seeing folks waving already. So, hello. So yes, we're going to talk about what's new in Compiler Explorer. And if I've got the focus in the right window, then I will be able to advance my slides. Okay, I'm going to do this through the medium of some background, where I'm going to start with some just quick fire questions about the project. So first of all, what is Compiler Explorer? Well, if you're attending a meeting called What's New in Compiler Explorer, you probably know. But just in case, it is a website that lets you type in C++ code and other languages and see how the compiler outputs its assembly from that. So as you type, the compiler runs, we show the assembly output, and an awful lot more. Why? Why would you want to do this? That's an excellent question. Compiler Explorer came out of the need that I had a number of years ago when I was trying to argue with my then lead developer about using some C++11 features. He was very conservative about enabling new things, worrying that they would slow down the code. At the time, I was working for a trading company. That trading company, latency was really important, so performance was key. And so anything new was treated with suspicion, probably correctly. There are some rationales as to why. But I was frustrated. I wanted to use C++11 features like range 4s. And so I knocked up a tiny shell script to compile code and show like some slightly massaged output from the compiler by, grepping out things that were unimportant and running it through cplusplus. And I was able to show that the source code for a iterate over a vector using the old school ways of size t, index equals 0, index is less than size, generated the exact same assembly output, or very close to it, as the range 4, which is perhaps of no surprise to us now, many years on. They're very equivalent. But it was an eye-opener. And I started running it interactively by putting it in a watch loop and then having an editor in the other window. And very quickly, I thought, this is cool. This is probably more useful than I thought. So I knocked up a little website. Anyway, that's the backstory. That's why it's really important for us back then, although it's used for a lot of other reasons now. When did this happen? So this was in 2012. So I was working for a trading company, as I said, and within a couple of months, I got permission to open source this internal tool I'd made. And on the 22nd of March, 2012, the GitHub repo was created, and Compiler Explorer, or GCC Explorer, or Interactive Compiler, even as it says here on this very first commit, was born. So you can actually check out the very first commit to the project, and it still runs with a tiny bit of tweaking, and it will show you something which looks like this. It's probably somewhat familiar to you. You can see that we have the left-hand pane with the editor and the assembly output, which is unfiltered. It's got loads of junk in there that's probably not very interesting, but we could choose a compiler and you could add in compiler options and things like that. So back in 2012, we supported GCC and Clang. Although it was called GCC Explorer, it did in fact support Clang from the outset. At least the first public version did. The GCC Explorer name kind of outlived its usefulness, and so I renamed it to Compiler Explorer, which is a lot more generic when we added more and more compilers and other things. And I initially hosted it on my own personal domain at gcc.godbolt.org, and I call it Compiler Explorer. Many other folks have decided to call it by the domain name that you're probably more familiar with, but it's Compiler Explorer, at least to me. Anyway, so 2012, we had GCC and Clang. It only supported C++. The output was unfiltered, although actually that was one of the first things as we added filtering. And probably the one and only thing that I thought of as being my contribution, other than running other people's code, is the syntax highlighting of the backgrounds that shows how the source code maps to the assembly output, the sort of synchronized color background. Everything else is just me running other people's code. The project was only 5,000 lines of JavaScript. It was just me, and it was self-funded. My wife was happy enough for me to spend a few $100 here and there to keep the thing afloat. Fast forward 12 years, and we're now at 2,800 compilers, more than 2,800 compilers. Although, in fairness, some of those are double counted. We count GCC both as a C compiler and a C++ compiler. But even if conservatively we've got like 1,400 unique compilers, we support 65 languages. We have filters, we have tools, we have diffs, we have IDEs, we have all sorts of things, which I'll show you in a minute. It's now 90,000 lines of TypeScript. TypeScript is a type-safe version of JavaScript, which means to say it's not really all that type-safe, and it needs to be compiled. So it kind of gets all of the worst things of C++, like slow compiles, and all of the worst things of something which doesn't really have types, but it's still better than pure JavaScript. And I'm very, very pleased to say that I have an amazing team of folks who help run the site, who do most of the work, and who are pretty much the only reason that the site keeps going is the volunteers. I'm here to pay the bills and sort of vaguely project manage things these days. And we also have loads and loads of contributors who come in and help, like update compilers and things like that. And I'm glad to say I don't actually foot the bill myself. The bill is covered, and more so by some patrons that I have and some commercial sponsors who support the site. So a huge thanks to both my team and anyone who supports the site financially. It really is far too much for me to be able to do by myself these days on all those axes. How is it working, or how does it work? This is a simplified diagram of what goes on behind the scenes. Each one of these boxes is either a computer or a set of computers or a service. And the intention here is not for you to look at it and not for me to go through this, because you're not really at a talk called How Does Compiler Explorer Work? But it has grown and grown and grown. And we have Linux machines, Windows machines that have GPUs. We have external access to Microsoft, where they run some of the compilers for us. We have a staging instance. We have a lot of infrastructure. So I'm very, very pleased again to have the support of lots of people to help me with all of this. And this is not who makes it. This is who is using the site. Developers, probably most of the folks who are watching this are developers. I use it in my day-to-day life. It's a real great way of not only seeing how the compiler works, but just testing out ideas. It's quick to compile small snippets of code. I can pick loads of different compilers, ones that I don't have installed. I can run some of the tooling that we've got there it's more convenient than running it locally, which is actually kind of an argument that our tooling needs to improve across the board. If it's easier to send your source code across the other side of the world to someone else's server and then have it sent back to you than it is to run it locally, then maybe we should be looking at our tooling. But that's a different topic of conversation. So developers use it for all sorts of things. Trainers and universities use the site so that it's a very convenient way of demonstrating parts of the language without showing lots of awkward things like how complicated IDEs or make files or running command lines from the client. It also means that at university, you can have a room full of students and say, just hit this URL and off you go. That is a lot more convenient than trying to get everybody set up. It's certainly for an introduction to programming course. And also, some of the tooling that we have is very, very convenient if you're trying to learn how compilers work behind the scenes. And we'll see some of those later on. I also know that security researchers have used the site. I've had a few people ask if they can train their AI to detect particular code snippets by sending known vulnerable bits of source code through all the different compilers we support. And I'm not sure how that came out, but I said that they were fine to do it. We have an API that they can use. And I'm really pleased to say that compiler authors use the site to both reproduce bugs or have folks who report bugs use Compiler Explorer to show that it's not just a problem on their computer. And that means that the compilers themselves are improving because of Compiler Explorer. And that is wonderful. I mean, not just because obviously but it's part of the ecosystem that helps compilers improve, which actually ultimately benefits me in my day job. the backstory. So there's a question about the backstory of why MSVC output execution has gotten removed. We can talk about that after. I'll get to that. If you want to hang out in Gather Town, we'll chat there. So the way that I want to talk about what's new in Compiler Explorer is through the lens of different people who might want to use the site. So I've invented some people and their theoretical use cases, and then I'll sort of like show the recommendations that I would have for them to be able to get the most out of the site and what it can do. And that will cover some of the things you've probably seen before, but also some things that are new. And even if you think you've used a lot of the site, you'll probably see something novel in here yourself. The first person we're going to talk about is Jordan. Jordan is a high-frequency trader and has been in a similar situation that I was when I invented the site. So he's sort of more focused on the performance, and he wants to be able to show his team that certain C++ idioms are in fact more performant, or at least as performant as doing it like the old way or the difficult way, and that you should be able to trust the compiler to do things for you rather than write it all out longhand. So we're going to start with an example here. I'm going to click here and hope that this also shows up. Hooray. So I am using the dark theme. If you haven't noticed, up here in the settings, more and settings, you can pick the theme of the system. That we've got a number of different themes. I've picked same as system, and everything's dark on my system. So if it looks unfamiliar to you, if you're used to seeing it look like this, it's because I am using a system theme that makes it dark. And I'm actually going to turn on the dark rainbow line highlighting color scheme. So we've got a slightly different thing. Hopefully, if this is awful to see, by the way, please put something in the chat and I will change to the light style. So this is the site, right? We're going to show a piece of code that Jordan maybe has in his code base right now, which for whatever important trading reason, he wants to sum an array. And the array has been given, and this actually already hurts me that I've forgotten to do this. That should be a const pointer, right? And it probably should be a span or something called like this. But let's just assume Jordan has an array and a number of things that go into the array, and he has to return the sum of the things that are in the array, and that we're not going to worry about overflow or anything like that. So this is the old way of doing it. There is a much nicer way of doing it down here using standard accumulate. But we want to show that we can use this because Jordan's lead programmer is very conservative and thinks that the int sum old school way is probably better or faster or whatever. So how might we do this with Compiler Explorer? So the first thing that I'm going to do is that I could just switch back and forth between these two implementations, or I could have a hash define between the two of them that toggles it back and forth. But I'm actually going to open up some more windows and I'm going to do some comparisons between them sort of side by side. The way that I'm going to do this is I'm going to remember that I'm on a Mac at the last minute and the keyboard shortcuts are all different. So bear with me a second. I'm going to copy the code and remove this from here. And I'm going to add a new source editor, plop it down here. So this is another copy of the editor. I'll just make this 22 as well. I'll paste in, whoops, again, you'll see me typing Mac related things that are, comment that in and delete that. So in this bottom one, I have this standard accumulate version. In the top one, I've got the old school version. Now, at the moment, we've still only got one compiler over here. So this is currently compiling. This is a little small, but it tells us that it's GCC blah for editor number one. And editor number one is this top one. So I can add a new compiler to the bottom, and I'm going to click and drag. And incidentally, when you click on these things, you can actually just hold the mouse down, and then that lets you choose where the output is going to go. So I'm going to put it down here, and I'm going to steal the same, whoops, again, with the keyboard shortcuts. I'm going to paste that in here, and I'm going to output this to be also 22. And so we've got the output of the two programs here. And that's kind of useful, I guess. I could scroll up and down and look and see if they look the same or different. I could actually put them side by side. So one thing that maybe you didn't know is that this is a fully tabbed sort of window manager. I can grab this window and plop it so that it's like a tab next to its own source code. And then I could do the same for the one down here. And now I could drag this whole window up. So let's do it like this. Up, up, and then put that next to it. And so I've got the source code in one tab and I've got its compilation in another. And that means I can have the assembly code side by side. Yes. Yeah. Also in GatherTown, absolutely, for how the short links work. Be delighted to explain that. So they look kind of similar to me on both sides, and that's kind of okay. I could sort of squint a little bit, but what we can actually do is we can add a whole new view from this very top level. Excuse me. And I'm going to add a difference view. I'm going to just plonk it in the middle, and I'm going to use another button up here. So again, it being a window manager means we have a maximize and minimize button. So I'm going to maximize this. Those other windows are behind this now, and this is a difference between the two. Again, let's just quickly zoom that in. By default, it actually picks the same thing. Obviously, there's no difference between these two outputs. But if I pick the right-hand side as being editor and compiler number 2, we now get an actual side-by-side diff. And you can see that there is a slight change in the number of instructions from left to right. And number of instructions isn't always a good example of whether something is faster or slower, but it's interesting, right? It's something to look into. But I know that for large arrays, the thing that's going to matter most is the inner loop. And I happen to know where that inner loop is, and it's down here at L4. And so if I compare lines 15 and through, 15 through 19 on this side with 19 through 23 on the other, they look very, very similar. And in fact, the only real difference is that a different register here, this RDX versus RCX. So they're essentially identical. And that might be enough for me to go to my boss and say, look, there's a little bit of change either side of it, but the core loop is identical. It's the same instructions, give or take a register allocation, which is different, which should have no impact on the performance. So that's pretty cool. Now, what we can actually do is go one further. I'm going to now pick up that code, and I've now got it in my clipboard, and I'm going to close down one of these, and close you down, and I'm going to change this to be an analysis window. So you can pick a different language. We've got many languages in here. One of them is analysis, which isn't a real language, but it lets you put assembly code in and then run an analyzer on it. So I'm going to paste the snippet that I got into this window and then add a compiler, which I shouldn't have closed. I'm going to pick the analyzer LLVM MCA, which is the LLVM project's machine code analyzer. Osaka is another one in here, and there are other ones available, but this is the one I know the most. And again, I will just zoom this into 22. And what this does is it does a kind of simulation of the code, assuming it's in a loop, and it does 100 iterations of that loop by default. And it says, if I were to run this code on some synthesized simulator of an x86, and I did 100 iterations, then it would be 400 instructions. That figures there are 4 instructions here. 4 times 100 is 400, but it would only take 110 machine cycles. And it does that through this analysis that you can drill into here. We can actually also tell it to do dash timeline. If I could type timeline, and it will show a timeline down here of the instructions and where they are in the pipeline and all sorts of clever stuff. Now, I haven't got time to go into details here, but this is a really cool way of showing that this would be I don't know why it's gone up to 143 cycles now. Never change things while we're going. That's really interesting that putting timeline in actually changed it. Oh, well, something's going on behind the scenes there. But anyway, this is a great way of being able to take this and go and say, like, not only can I show that the code is equivalent to use standard accumulate to using a regular int-based loop, but I can actually tell you how long it should take now. Now, this doesn't take into account cache and all that kind of stuff like that, but it's demonstrating another feature that we have here. So I'm going to go back now. Yes, analysis view. And so that's one way that you could show that modern compilers are great at generating the kind of output that we want. Another thing that we might want to do is show the compiler's ability to inline. So this is a bugbear of mine. So you might start to realize that Jordan is kind of me, really. So I'm going to open a new tab, and I'm going to go to Compiler Explorer, and I'm going to reset. I'm going to go up here and I'm going to reset code and UI layout. So I'm going to, from scratch, so wish me luck if I remember how to do this, I'm going to try and demonstrate inlining, except I'm going to show that inlining across translation units is possible with modern compilers. So one thing that you may do is for very high performance code, or for other reasons, you might put the implementation of all your functions into the header files so that they're available to all other translation units and they can be inlined. And that's great. It's an important thing to be able to do, but it's not very good if you need to change that implementation, because if you change that implementation, your entire project has to rebuild because you've just touched one of the header files that's important. So it's nice to be able to hide away the implementation in the CPP file, in the translation unit. But you're now giving up the ability of the compiler to inline across those translation units, except modern compilers can actually do this. And so if I wanted to demonstrate to my boss that it would be okay to pull things out of header files where appropriate, I would want to do something like we're going to do now. So I am going to use this square example you've all seen 100 times before. I am going to add a new source editor over here. And this source editor does not inherit the size, unfortunately. And I'm going to assume that on the left-hand side, this is like the implementation file. And on the right-hand side, this is like some main program. So because I'm not going to do headers, I'm just going to say there exists a function called square. And if I could type, it would help. It takes an integer num, and I'm not going to define it. I'm only declaring it here. Now, this is just because I don't have time to do all of the header file inclusion stuff. And then my main function is going to be returning the square of 10. Okay, so nothing is compiling at the moment because I don't have a compiler. And if I were to actually add a compiler, it would compile each file individually, which wouldn't work in this instance. That we would see that there would be a link error if we tried to link it, or it would definitely not be able to inline square because it doesn't know what square is. They're two independent compilations. But a new and awesome feature that we have is to be able to have a tree or IDE mode. I'm going to snap this to the side here. And now you can see that we have a little bit more of a traditional IDE kind of view, where on the left-hand side, we can see all of the windows that we've got open, and we can actually join them to a build. And in fact, by hitting either this plus button here, or by hitting Control S to save, which I'm going to do over here, I'm going to save this file as square.cpp. And you'll notice it's appeared in this included files over here on the left. And this file over here, I'm going to save as, please work, save. I'm pressing the wrong key. Again, I had to switch to a Mac at last minute because my Linux machine wasn't working. Main.cpp. And now they're both in the build. And then for the purposes of what I would like to do, I'm going to use CMake to build both of these things together and then link them. So I'm going to tick the CMake build box here, and I'm going to say that it's going to output something called, let's call it square. But now I need a CMake lists. So let's add a new source editor. And this one I'm going to save immediately. And I'm going to save it as CMake lists.txt. And this is where I have to hope. And you'll notice it's changed the type to CMake up here. So this is project. We're going to call it square, add executable square. And it's going to be square.cpp and main.cpp. All right. Nothing is happening yet, though. And we're going to 22 this one so you can actually read it. Okay. I'm going to stack all these things up together so that all of the three tabs are here. And now I'm going to add a compiler, but I'm going to add the compiler to the IDE window, which means that it will compile the entire project. So I'm going to pick up this compiler. I'm going to drag it over here. This chap was going to be smaller. And this one is going to be 22. And so what we've got now is the entire program. So first of all, we're building an entire program. And in fact, if I open the output window down here, you can see there's CMake doing all of the CMake things that we know and love. It's doing detecting, it's building two different programs here, files, square.cpp, main.cpp, and it has linked it, and then it's disassembled it over here. So that's pretty cool. And again, like all my source code are in these three tabs here. Let's take a look. On the right-hand side, nothing particularly exciting has happened. Let's turn the optimizer on. I know we've got CMake build type equals debug over there, but I can override it by putting O2 in here. And then we can see that square, the function square over here, is just doing an imul, exactly as we'd expect. It takes the input, multiplies it with itself, and then returns it in EAX. Great. And then we look at main, and main says exactly as we've asked it to do, put 10, which is nor XA. If you mouse over nor XA, you can see it says 10 at the top there, and we get all of the various different interpretations of what that might be. 10 is A is some crazy floating point number. But then it just jumps to the square, which means it hasn't inlined that function. Because if it had inlined that function, we would hope that it would be smarter than actually doing the multiply operation. So now we finally, having done all this setup work, have got to the point where we can demonstrate that if we turn on FLTO for link time optimization and hope that it works, we can see that now main has in fact inlined the square function and has output NOR-X64, which is indeed the 100 that we would expect. So this is a way of using the IDE mode to build an entire project and show that project level settings can take effect. Cool. All right, let's move back to the presentation. And oh, whoops, yes, aha. I knew I should do this type of thing. Let me bring the window back. I'm glad I have my notes so that I didn't look at them. So you may be thinking to yourself, that's great, Matt. There's a lot of things there. There's a lot of windows I have to move around. It just took you 10 minutes to demonstrate this to us. How on earth am I going to remember how to do all of those things? Well, I have good news for you. I'm going to actually reset the code and UI layout. So we're back to good old-fashioned default output. And I'm going to show you that we have these things called templates. If you click up here, these templates do not have 1,000 line error messages. They have nice pictures. And what these templates are a way of getting the site into a particular configuration conveniently. So we've got these pre-canned diffs of two sources, which shows, differencing the output of two sources, much like I did earlier. We've got two compiler outputs being different. We've got a C++ CMake example. And so I'm going to click this C++ CMake, and you get dropped into a version which shows all of the features I just discussed and more. This actually has some files that are inside the output that you can open up as a file. So like this resources hello.txt here is says hello world, and you'll see the output of the program down here is actually reading that file. So we actually upload all of the resources and let your program run on those resources if you need to. It's also showing some library functionality that we'll cover in a second. So there's a lot of cool features here that are pre-done. So you can bring up the Ada IDE if you want to go and see what Ada looks like. And you can actually save your own templates as, my cool template here. And then you can come back to it. Now, you can, of course, bookmark a short URL. If you go up to the top here and do a short link and you copy that to the clipboard, or if you bring it up here, you can copy this. And that's another way of getting similar functionality. The templates themselves are saved in your browser storage. So if you are one of those people who clear their browser storage regularly, you probably want to just have some short links saved. But it's not a bad way to get started, or even just explore what we can do and some of the other things that you maybe didn't know that we supported. All right. Did we go through all those things? I think we did. Good. All right. That's Jordan. Let's talk about Mason. Mason's another user of the site. Mason works for a local community college and has a YouTube channel. And they spend a lot of their time trying to bring the delights of programming to the masses, be they folks who are already interested in it, people who don't really know much about programming at all, or folks who are trying to dig more and more into the world of what goes on behind the scenes. So what kind of things might you do if you were a trainer like this? Well, the first thing, obviously, is teaching. So what you might do is hand out a short link, such as I've just clicked on, to your students and say, hey, I would like you to fill in this function here. I've given you a function which is bool contains 0, and it's given a reference to a vector of integers, and I want you to return true or false, depending on whether or not there is a 0 in that array of integers, that vector of integers. And, if you're old like me, you'd start doing something like for auto x, and excuse my short things, variable names here. If x is equal to 0, return true, return false, right? That's a way of doing it. And you can see the code is generating on the right-hand side. And we're going to ignore that for now. But, this is not the right way to do things these days. There are better ways of doing this. So what if I were to do return stud ranges contains b, 0. Is that the right one? No, it's fine. Sorry. Haha. See, I can remember this. Find b, 0 is not equal to stud n of b. Okay, well, we've got a problem here because it says there's no member named ranges in namespace stud. So let's include range. Is it range or ranges? I can never remember. Ranges. Okay, well, even though we included ranges, it's telling me, and it didn't go wrong with that, it's telling me there's no member named ranges in namespace stud. And that's because our compiler needs to be told to enable all of the cool new features that C++ 2a or 223 or whichever one it is needs in order to see this ranges, even though the file is physically present. Now, I could fiddle around up here and try and work out what the right command line flag is, but I'm not even sure what it is. So how might I go from here? Well, we have a new feature called overrides. And if we click the overrides button here, which has this little tool next to it, we can configure the compiler in a new way. One thing we can do is we can add compiler environment variables. This is not so important for C++. I don't think there are many C++ compilers that care about environment variables when they're compiling, but there are other languages that do. But we also parse a subset of the command line parameters of the current compiler, and we pull out, for example, all of its supported target architectures. And we can now see that Clang support all of these different kinds of architectures. And if I tick one of these, it would put the right command line flag on to turn that architecture on. We can change which tool chain this Clang is looking at. If you might know, by default, Clang on Linux at least uses GCC's C++ library in order to be ABI compatible with the other programs on the system. But you can pick which version of GCC. We choose one for you. We choose the latest one. But if you need to pick another version, you can go through the thousands and thousands of possible combinations of other GCCs that we have available. And more importantly, for what we're doing right now, we parse out all of the supported standards. And so I think I want probably C++2B, the working draft for ISO C++ 2023 DIS, whatever that is. I'm going to click that. And then behind the scenes, when I close this window, we have to hope that it now compiles. Hooray! So now we have a working compiled version of the code. And that's awesome. We don't know if it's right or not. But right now, we're sort of faced with this assembly output, which is a little bit scary. So we're going to talk a little bit about the assembly, and then we're going to get rid of the assembly, because when you're trying to teach folks, then you probably don't want to be pointing them straight at assembly. I mean, I probably would, but that's just me. So before we move away from the assembly view, there's a couple of things I want to show. First of all, even if you don't know what half these instructions are, you can mouse over them. And for x86 and for, I believe, ARM, and coming soon, some of the RISC-V, I think, we have support for parsing out the manuals for these things. And so you can mouse over it and see that this is what the instruction does, sets the destination operand to 0 or 1, depending on. You can also right-click and go to View Assembly Documentation, where we get more information. And ultimately, you can click on this to go to the website where we scrape. So that's one thing. And then another thing is that some people are more visual learners. And we have a way of showing the output from this. So up here, we've got these two different things. We've got Add New and Add Tool. Add New here adds a new thing which kind of plugs into the current compiler. So these are all to do with the current compiler or very close to the compiler, whereas adding a tool adds something which runs on the output of the compiler after the compiler is finished or is independent of the compiler. So that's why we separate these two things. I realize it can be confusing. So I'm going to add a new control flow graph, and I'm going to plonk it down here, and then I'm actually going to maximize it, and then I'm going to reset the view, and I'll zoom around a bit. And what this is another way of showing the output from the compiler. And this is showing the control flow. So we can see each basic block, each set of instructions that run from beginning to end without any jumps. And then at the end of each basic block, there are one or two outs. One is if the branch is taken, one if the branch is not taken. So we can kind of see the flow here. If we were to follow the red arrows, we would be falling into the blue. And then this is it falling into the comparison. And then if it went through the green line here, that's it looping back round to the top. And so you can kind of get a view of like what's going on. And even if you don't fully understand what all the instructions are doing, this is another way of visualizing the same thing. So let me close that and go back to this. Again, we can run the code these days, like I think we showed. I can execute this code and it would tell me, oh, there's no main. I'd have to write a test. So luckily, here's one I prepared earlier. I'm going to go to execution. So now we've got this bool has 0, and I've used a stood span now because that's a lot better. And it's using ranges find up here, and I've written this little main function here. And it's not that useful to see all of this assembly output, especially now we've got like trying to print out stuff in here. So I'm going to turn this output over here, this window, into an executor, which we can tick the execution button down here, but I'm not interested in this assembly view, and I want to have more control over the output. And the way that we've tried to do this is instead of cramming all of the functionality that you want when you're executing your code into the same window as this assembly view, is that we've created a new view entirely. That view can, excuse me, that view can either come from you adding a new execution only view on the left-hand side here, or on the right-hand side, you can say, I want this view, but as an executor. And so I'm going to add a new executor from this, and I'm going to drag it up to there. Close the other one. So now, and as always, we've forgotten the size. We're just compiling and running the program. We're not showing you the disassembly. That's not very useful. Here it looks like it's working. My little test case here that has a vector of 0, 1, 2, 3, 1, 2, 3, 4, 0. In fact, has a 0 is true. And then if I were to get rid of the 0 over here, it would compile. It would have a think about it, and it would say false. Okay, but that's not very satisfying because, as you can see here, I've totally punted on actually printing out the vector, which would be a nice thing to do, right? I would love to use std print here and all the good stuff that comes with it, but it's not supported in GCC 13.1, which is the version that I've used here. But I do know where I can get it from FMT. So I could include format or FMT for format.h. But there's no such file directory because I haven't got format.h. But it would be really cool if I could get access to it, right? Luckily, we have some libraries available. And by some, I mean quite a lot. So if you click the little library button over here, which will look like a book if you haven't got space on your screen, this pop-up will appear. And you can see we have many libraries. The vast majority of them are header only, but there's still a substantial number for which we will build and allow you to link against too. And I'm going to search in here for format. And here is results for FMT. And I'm going to say I want the 10.2.1 version of format. And now that's available on my path. I'm also going to hit the star here. And it's remembered as a favorite so that I can come back to this a lot quicker. Again, this is stored in the browser. And if I was on my laptop, my non-Mac laptop, where I would have had some of these things set up to demonstrate, but I'm not. So there's format 10.2.1. Incidentally, you can do the same with compilers. You can make compilers favorites. So I can tick the box here that makes GCC 13.1 a favorite. And now it'll always be at the very, very top, along with all the other favorites that I have. But now we've got format available. Let's quickly do FMT print. And what do we need to do say? We want to say vector. And then we need to do two of those because we have to escape them as a 0, question mark, splat, splat. And then what do we need to pass it? We need to say FMT join I with, I don't know, comma, and then has 0. Oh, I need to /n on there, don't I, as well? Has 0 I, right? And let's get rid of the std cout and see if I've been able to type correctly. What have I missed out here? No, it worked. Hooray. Good grief. Phew, just took a moment. And so now we're actually seeing vector 12340 has a 0 true. And I'm sure there are much better ways of doing this, of course. We can get rid of the 1234 and it'll say has a 0 false, hopefully in a few seconds' time. And of course, if we really wanted to do this properly, I could go in here and let's look at something like catch2. And I could actually use catch2 and write actual unit tests that failed correctly and have nice outputs. Yes, let me just quickly check my list of things. Yes, okay, we've done everything. I think now I'm looking at the time and I'm thinking, gosh, this is going awfully quickly. So let's change tack a little bit. And so as well as showing that just actually how to program in C++, there are other aspects of the site that are interesting if you're trying to teach more like how things work behind the scenes. So let's have a look at linking. So this is something that I do quite a lot is that, in fact, you saw it earlier, I will sometimes use extern int some function, and then I'll call that function even though it's not defined anywhere. And that's really useful for like just saying it's not important right now what that function does. I just want to have the code for something that doesn't exist. But you can see that we output this text on the right-hand side. But it'd be interesting to see what it looks like to get the binary output of this this function, even though it's not linked. Now, the way that we used to do this is we had this thing called compile to binary or something. Actually, I forget what it used to be, but it was the equivalent of this link to binary option. And if I click it here, you get the please hold, you get the error that you'd expect. You know, we're trying to build an executable and then disassemble it, and it's got an undefined reference to some function. Fair enough. But if you're trying to teach how linkers work, or how operating systems conspire with linkers to get all of the symbols found, it's useful to be able to look at the .o file. And so we now support this compile to binary object, which does exactly that. So if I compile to binary object, we will compile and show you all of the opcodes, 4883 EC08 apparently is sub RSP, 8. Great. And you'll see that there is the calls to functions that don't exist yet. And we get to see a little bit behind the curtains in how this stuff works behind the scenes. So you'll see that it says call 9. Well, 9 is the next instruction. 9 is the next instruction, which is not true, right? We're not calling the next instruction, we're calling some function. But the reason it says call 9 is because in x86, the call instruction has a relative address, and the address is relative to the beginning of the next instruction. And at the moment, we don't know where that function is. We haven't linked it yet. And so the instruction is actually E8 for call, and then 00000000, 4 bytes of 0, saying that there's a 32-bit offset here that I don't know where it is yet. And by default, obviously, that will mean an offset of 0, which means the next instruction. But we also parse the output of some of the symbol table. And inside that symbol table is a reference to the linker to say, hey, please find something called sum function. And when you do find it, there's some function here, get its address -4 and poke it in at address number 5. And so this RX86-64-PLT32 thing is an instruction to the linker to do this work. And so we'll come along and it will replace these 4 0 bytes with the actual offset to the function that you want to call. And so that way we can show, and Mason could show their students, that this is what the linker is going to do behind the scenes. And we can go a little bit further than that even. I can add a tool, and all of the familiar Unix tools like NM, which reads all the symbol table, can be run on the output. In fact, if I zoom this in here, here it is with, showing that there is an undefined reference to _Z12 or Z12. Gosh, you can tell I've been in America too long. _Z12, some function V. I can still pass command line arguments. I can click this and then I can do -C, which means demangle. And you'll see that, yes, it's an undefined reference to some function. And we've got a number of things here. We've got coverage, we've got readable, strings, and other things that you might be interested in seeing. But again, we're running short on time, so I'm going to zoom on to the next thing. So that's linking and running some of the tools. If you're teaching anyone how to program these days, I think you should tell them about static analyzers. And so this is an example of me running a static analyzer. So I will run clang tidy here. So this is a piece of code. It's just made up. This is obviously not a very good example of how you should validate a user, but assuming that we can get the hash of the password that they supplied us and look it up, this is completely okay code. But if you're looking at it like I look at it, you're probably starting to twitch. There's something that's not quite right. If I were to add a tool, clang tidy, and I'll add it down here and get rid of you. Oh, I probably need you actually. Hang on, there we are. Okay. And then I've forgotten how to use it, so I'm actually just going to run it with --help here. And it is --checks equals. That's right. Okay. So --checks equals, and I happen to know the thing that you can enable thousands and thousands of checks, and it will be too much for us to look at it because every single piece of code has hundreds of checks. But if I say perf star, it will enable all of the performance checks, which is the ones I'm interested in. And then you can see here that it's saying, hey, look, you should probably pass these by reference because they're only copied. And all you're doing is copying the data twice unnecessarily, which is perhaps what all of you are shouting at your screens right now. Why the heck is this not const string amp? And so clang tidy has your back here. And there are hundreds and hundreds of other really useful warnings that clang tidy can provide for your code. And so as a trainer, you would want to be able to demonstrate that too. Very quickly, we also have some commercial tooling. So one of our sponsors, Sonar, let us run their linter. And this is an example that I found from theirs. I haven't got time to go into it, but this is how to misuse concepts. You're not actually using the concepts you think you are if you're doing it this way, which you can have a laugh at later if you want to look at the slides to see what it is. But if I add Sonar as a tool here, you'll see that Sonar will pretty quickly tell us that these two things here, this stood as integral and stood as same, that's not how that works, is what it's saying in a very long-winded way. It's saying these are unevaluated. This should probably be something like that, I think, if I remember rightly off the top of my head. Oops, I could actually type code and look at my keyboard at the same time. Is it going to work? No. Okay. No, it's not even requires. It's just equals that. Right. Please hold. Yeah, so it's now only complaining about the second thing. So anyway, that's Sonar. Okay, so that's Mason, that's training. What did we show? We went through the assembly tooltips. I showed you the control flow graph. I showed you some of the binary tools. We looked at the overrides, which lets you set all of those extra fancy things. There's an equivalent also for executing the code. I should have showed that as well, but you can set environment variables and other flags for the execution environment. In fact, no, there is. I will go back to that. Hang on, let's go back to that quickly, because it's too cool not to show. So let's go back to execution. And if I turn this output, no, where am I? Gosh, add new, execute from this. This is where I've gone off topic. If I go to the runtime tools, we can actually turn on heap tracking, and I can actually turn on a graph of the heap. Now, this is not a very exciting example because we don't really allocate anything. But now when we run the program, we run it with heap track, and there's a little button that pops up here. And then this is too small to see on the monitor, and I can't find the zooming in button on my screen right now. But you get the idea that it pops up a view where you can look at where allocations are happening. And we have some other things. I've got it. Where is it on my list here? We've got a time trace in one of the other compilation things, but unfortunately, I don't have a slide for that. Anyway, so yes, we have overrides. We've got static analyzers. I've shown you how you can do execution only, and that we have lots of libraries. And there was a question earlier, which libraries do we select to support? Whoever sends us a PR gets it. We've made the process as easy as we can. It's not, I won't say that it is easy, but it is entirely possible for individual library authors to send us a pull request in a couple of repositories, and that will get the library installed and available on the site, usually within a couple of days. Seeing people are typing, I'll try and get to those questions as I go, but otherwise we'll have to wait till Gather Town because we've got 13 minutes left and I've got more slides to go through. So let's talk about, should add a tip of the day window. That's a great idea, actually. That's a fantastic idea, just mentioned in the chat. Right, 1 second. Right. So, Joanna, let's talk about Joanna. Joanna is one of those developers that loves to, I'm going to say misuse, but let's say use the compiler features in ways that no one else has ever thought of before. There are, so she's always trying to find these new and exciting ways to compile C++ to get things that you didn't think you could do in C++ done. And she's also really interested in the kind of optimizations that compilers do. She's essentially a compiler adjacent person. And she has a very cute dog. And let's have a look at what the kind of things that Compiler Explorer can help somebody like Joanna. So I haven't got one of the more complicated things that Joanna probably would look at, and most people would know about this particular issue anyway. But here, for example, is the C++'s most vexing pars. So if you are torturing the language and trying to get the weirdest things to compile, you might hit things like this. It's not a very good example, but it's an example nonetheless. And so what this is I'm trying to cast this as an int. I'm doing int of f. That means, cast f to an int in a terrible way, and then I'm assigning it to this int as int, and then I'm returning it. But that's not what's happening. Actually, compilers will tell you, if I mouse over this, it says, hey, it was disambiguated as a function declaration, which is a bit of a hint. But yes, there's no conference without this. But, it might be interesting to see how this comes about. One of the things that we do is we support introspection into Clang's abstract syntax tree. So if you have a Clang compiler selected, you can add a new AST. I'm going to add the AST. Where am I going to put it? I'm going to put it down here. Right. And I'm going to zoom it in because, of course, I haven't got my default set. My mouse wheel works. There we are. 22. And so what we've got here is an internal representation of Clang's abstract syntax tree, which is hard to say. And as you can see, just like any other window, as I mouse over it, the different parts of the expression highlight where they came from in the source code. And so what we can see here is this whole program has been parsed as a translation unit, which is a function declaration, makes sense, of which has a parameter value, which makes sense. And it has a compound statement. Yep. So far, so good. And then it has a declaration statement. Well, that's not what I meant at all. I wanted to define a variable here. And it says it's a function declaration. And so this kind of explains a little bit about C++'s most vexing parse, and certainly gives you some way of introspecting into what the heck is going on inside the parser. Obviously, we have to fix it. There are much better ways of doing this, obviously, but let's just fix it because it hurts me to look at it. And there we are. Oh, it's still complaining about that. Oh, no, it has in fact finished. And now that it parses, it's fine. And it has in fact been parsed as a variable declaration with an initializer list and all sorts of complicated stuff going on there. So that's the first thing that we could use this approach for. And if I could find the back key, that would help. So parsing, check. We can go and look at the internal state of the compiler and maybe infer why our esoteric edge case of C++ isn't compiling the way we thought it should do. Maybe find a bug. Another thing, and now this is where, again, all of these people are different sort of parts of my personality as much as they are any other real person. We might want to look into the internals of a compiler. Now, this is just my absolute favoritist thing ever about what compilers can do these days. And so no talk would be good without mentioning something smart that compilers do. So imagine, for whatever reason, you wanted to know how many 1-bits there were in this value, this 64-bit value here. You might write code such as I've written here, which is to say we start with a count of 0. While our input value is still non-zero, we know that there's at least 1 bit set. So I'm going to increment the number of bits set. And then I'm going to use this cool trick. It's one neat trick for clearing the bottom set bit. There's the first bit counting from the bottom that is currently set. We're going to clear it, and then we're going to go around, and we just keep going around until there are no more 1 bits left, and then however many times we had to clear a bit was how many bits there were set, right? And so that's pretty cool and all, but if you look on the right-hand side, it has been completely replaced with a single instruction, pop count. There is an instruction in x86 that does this operation, and the compiler is smart enough to read my code, which has a loop in it, and determine that it is in fact a single instruction. We're not going to talk about the C move. That's a whole other talk. But let's just assume for the moment that it's just this pop count. And again, we can mouse over and see this instruction calculates the number of bits set to 1. Hooray! But how did it achieve this masterpiece? How might we find out? Well, one way to do this is to look at the optimization pipeline. So again, this is for LLVM. We call it deep introspection, of what's going on inside LLVM. I'm going to put this window here, and it's going to tell me error, which it shouldn't do. Oh, phew, it's never do live demos, and this is a whole live demo. I'm going to maximize it so it takes up the whole screen. So again, what we had before is behind this window. And I'm going to zoom this in to 22 because 22 is the magic number. What we're looking at here is the one and only function that's defined in this file. And we're looking at a full report of everything the compiler did to the code. On the left-hand side is a list of all of the different function passes that the clang optimizer did. And there are lots and lots and lots and lots of them. As you can see, there's literally hundreds of passes. And what generally happens inside a compiler is that there is an intermediate representation of your program. In Clang, it's LLVM. This is the low-level virtual machine, which is what you can see on the screen behind me. In front of you, in fact. And each pass makes some kind of small change to improve the performance or to annotate the code or whatever. And that's what's happening on this left-hand side here. What we do is we highlight in green any of the passes that actually change the code. And then this is actually a difference view. So if I click on this SROA pass, which is the scalar replacement of aggregate pass, I just happen to know, we can see that the code changes quite a lot. I'm going to zoom out a tiny bit so we've got a little hope of seeing a bit more. Maybe that's still big enough. But you can see some big changes happen. A lot of stuff moved from the left-hand side and changed to the right-hand side. Some phis got added, or fees. Some people could say fee, and so on. And anyway, this is, if you were a compiler author, you would know what all of these things do, and you can click on them all and look at the various differences that are happening, if something happened there. And then you'd scroll and scroll and scroll. And if you're an interested person like I am, you would take the time to click around these until you eventually get to the pass called loop deletion pass. You'd click on that, and you would see that on the left-hand side, there is a while loop, while body, and all this kind of nonsense. And on the right-hand side, that loop has been deleted. The labels haven't been, but the loop itself has been deleted and replaced with this call to llvm.ctpop.i64, which is the internal way of saying, hey, the loop deletion pass has determined that there is a built-in magical function, which maps to an instruction in this case, that actually does the work of this 64-bit population count. And that's marvelous. Now I can go and Google, I can go and find the loop deletion pass, I can go and find the code, and you can go and see how it's done, which is really clever. So that is, we're hoping to get more. We've got similar things for GCC, but we haven't got them quite as to the same level of finesse. But nonetheless, you can have a look at the compiler internals. Very quickly, as we're down to the last few minutes here, one of the other things you might do if you're into like all these templatey tricks and all of these other bits and pieces is to actually want to compile your code like this std ranges find on many different compilers to see which ones actually support the thing that you're doing. So I'm going to close the compiler here, and I'm going to add something that is the conformance view. And what the conformance view basically is it allows me to select lots of different compilers and paste in all of the flags that I had. And unfortunately, I don't have a lot of time at the moment. Let me just turn on, I'm picking random compilers here, as you can tell. And every time I change anything in the code, I can add up, I think there's a couple of dozen of these things here. So that won't work, obviously. So like this doesn't work on AVR GCC. It's doing the compile. I can look at the error messages. I can open a tab that just has that compiler in it. The red means that it failed. The green means that it succeeded. The amber means there were warnings. And so you can fiddle around with your code to your heart's content. And obviously, if I break it on purpose by typing rubbish into it, they'll all fail. So this is a great way of trying out code on lots of compilers. And of course, you can set up one of these with all of the compilers you care about, and then save a short link or a template. And then you can come back to it and use it as your kind of workhorse for, does this work on all the compilers that I care about? And you can also help, run up our Amazon bill by doing lots and lots of compiles at once. Okay. So we covered the AST view, the LLVM pass viewer. You now know where to look to go and find the equivalents for GCC, and we looked at the conformance view as well. Now, in the 3 minutes remaining, we're going to talk about the last person who uses the site. We're going to call that person Matt. So Matt is a late 40s software engineer who somehow can't give up on his childhood obsession with 8-bit computers that he had when he was growing up. And so what Matt might want to do is, for example, take some code for the BBC Micro circa 1984, like this, although this is not actually from 1984. This is more modern than that. This is my friend Richard's code. Matt's friend's Richard's code. And it's cool and all. It's written in assembly because, it's a BBC Micro, and we can compile it, which is to say we can assemble it over here. And indeed, we've assembled it into the equivalent code with all lookup tables and everything. And that's great, but I'm going to reload the page because once it loads up, there's a little thing at the bottom right-hand corner which I can click, and it actually fires up an emulator with that code. And so you can see it running on this BBC Micro, as you can tell, with this little MicroVitek Cub monitor. For those of you of a certain age, this is probably more memorable than not. And yes, you can run an emulator from a compiled version directly in the site. We support also, I think, we've got a Nintendo emulator. We've got a Commodore 64 one, I think. We've got a Sega Master System emulator. And some of the compilers even can target it. I forget exactly which one. We're running very low on time. But there are, I think you have to select C. And if you do 6502, yes, we've got CC65 in here. I think there's even a C++ compiler that supports it. But I should have noted that down beforehand. Anyway, there is more. There's more. There's only 60 seconds more, but there is more of this. So very, very, very quickly, we have public statistics about what's going on the site. If you hit stats.compilerexplorer.com, you can see it. We do support execution on GPUs these days. So if you want to run some CUDA code on an actual real GPU, you can. We support some amount of Windows execution. If you use MinGW, then you can run on your program on one of our Windows hosts. And yes, the results may vary because as noted before, the MSVC. Thank you. Partouf has put into the chat. Partouf is the person who knows more about this than me. I don't know why I'm even talking, and I should put Partouf up here. But the supported emulators link is in the chat, and we'll post it somewhere else too. I think that is all I've got here. Yes, no, I've got future dreams, don't we all? Obviously, more compilers, languages, platforms. It would be cool to support ARM. Something that's asked for a lot, something that would be useful in my day job would be to have live updating links. That is, links that I can share with somebody, and then we can both type in the window, or at least one of us can type and the other can see it change as they edit, but that's a lot of work. And then the confluence of all the things that I love would be to take emulators and simulators, performance, compilers, optimizers, put them all into one thing and have like a fully featured x86 or similar simulator that can show, just like the OSAK ACA and the LLVM MCA example, but interactively show what's going on inside the CPU as you're single stepping through the single C++ code that you wrote. Okay, last slide. Thank you for staying with me on this hour-long journey. Huge thanks to our commercial sponsors, Intel, Google, Solid Sands, Sonar Lint, my patrons and my GitHub supporters, and anyone who supports us directly on PayPal. Of course, a huge thank to all of the implementers, in Partouf amongst them, who's in the chat channel right now. You can say thanks to them too, for doing all of the hard work and me letting me take all of the credit for it. And thanks to my employer, Aquatic, for letting me take a couple of hours out of my day to come and speak with you all. If you're interested in this kind of stuff, you might want to ping me directly. We're always looking for smart individuals, and that's how I pay for the time off. So that is me done. Thank you very much. I will be in Gathertown to answer questions immediately after this. Thank you very much indeed for your time.